All right, in our second lesson on work and energy, we're going to look at the concept of network, meaning we have multiple forces now acting on an object, and we want to calculate the total work done. So the total work done is the net work done. And we'll also talk more about the meaning of negative work and energy being transferred away from an object. So we'll see how that works out. Okay, so let's say we have this example that we're looking at down here. Multiple forces. We have a 5 Newton force, F2 6 newtons, F3 2 newtons, F4 2 newtons. You're given the angles at which these forces are acting, and we want to know the net energy transferred to this object, this mass, as it moves from its initial position here to the final position, 40 not newtons, 40 meters, so change that to meters, 40 meters to the right. And we're just going to calculate the energy transferred by each of the forces individually, and then add and subtract the energy in and the energy out to get the net energy transfer. So we're just doing our same dot product that we've been doing, F dot delta X, for each of the forces individually. So I'll leave it to you to confirm all of these dot products. I'll take you through the first one here with the magnitude of the force, F, magnitude of delta X, 40, and cosine of the angle between the two is 0, and that's why we get the positive 200 joules. So F1 is transferring 200 joules to the object. So if F1 were the only force acting on this object would be speeding up, moving to the right, and it would have gained 200 joules of energy going over the 40-meter distance that it moved to the right. So you can confirm the 6 Newton value of positive 154. Please make sure that you understand why the dot products work out the way they do. But let's take a look at 3 and 4. Let's take a look at 3 quickly. So for force 3, notice we have to be careful with our angles, because when we calculate the work done, it's F3 dot delta X, so F3 is 2. Delta X is still 40 meters, and it's magnitude, so we don't care about positives and negatives for the F's and the delta X. But now we have to look at the cosine of the angle between the two vectors. So my delta X is to the right, my F2 is here, so this angle is going to be 180 minus 20, or 160. So you definitely have to be careful with your angles that you put in the cosines. And of course, that cosine of 160 gives us a negative when we calculate it on our calculator. So that means F3 is transferring 75.18 joules away from the object as it moves from its initial position to its final position. And that should make sense, because the object is moving to the right, and F3 is basically pulling to the left. Not all of it. How much of it is pulling to the left? Well, F cosine theta of it is pulling to the left. So this is why dot product is very useful in calculating energy transfers. So even if there were no other forces other than F3, if the object, the mass, was going to the right, F3 would be dragging it to a stop eventually, but over this 40 meters, it would have removed 75.18 joules of energy. And then we can see F4 is also removing energy. Cosine of 180 is negative 1, so there's negative 80 joules removed by F4. Well, we have competing forces and competing transfers of energy. So 1 and 2 are transferring energy into the mass, speeding it up, and 3 and 4 are transferring energy away from the mass, trying to slow it down, and the net work done is simply adding up all these values, and we see the net energy transfer is positive 199 joules, so close to 200 joules of energy transferred to the object. This object is speeding up, and if I'm given individual forces, I normally like to calculate net force this way, so I have a clear understanding of what the individual forces were doing during the process and where the energy transfer was really coming from. However, if all you want is the net force, it is sometimes more convenient to just first calculate the net force, and then you can just do net force dot delta x, and that will also give you positive 199 joules. And I invite you to try that if you want to do your tip to tails, or even just do it in x hat and y hat. Calculate a net force value and do F dot delta x. It absolutely does work out. Well, the last thing we have to talk about in terms of network is, what if you are given the forces in component form? So what if now my displacement, delta x, so I don't have a delta x, I have a delta s, but what if that displacement, delta s, now replaces my delta x, so my network is F dot delta s. Now it's very easy to calculate the net force. I can just line up my x's and y's and calculate the net force. In the x direction is 4, positive 4. My net force in the y direction is 2 minus 6 minus 7 minus 2, so minus 13 x hat. And then just do my dot product based on F net dot delta s. And remember, when you're taking dot products distribute through. So I'm going to dot the 4i hat with the 5i hat. I'm going to dot the 4i hat with the 6j hat. But anytime we dot a vector with a vector that is at 90 degrees to it, cosine of 90 degrees is 0. So we lose the terms that would have x, y, x, z. So the only thing we're left with is x, x, and y, y. And my two x's are in the same direction, so I get a cosine of 0. My two y's are in opposite directions. The 13 is to the left, and the 13 is down, y direction, down, and the 6 is up, so that's why we get the cosine of 180, and I get 20 minus 78 is negative 58 joules. Notice there's no, even though I was doing x with x and y with y, I do not put an x with my calculation for the joule value based on what those x forces were doing. Energy is a scalar. By far the biggest mistake I'll see students lapse back into is putting x's and y's here in their answers. So please try to be aware of that and fight the urge to carry the x's through. If you notice, what we have here is a negative joule value for our answer, which we know that this object was slowing down. Energy was being transferred away from the object, and I should have I don't know what that decreases, so speed decreases. It would be slowing down. Okay, so there we have some more examples of mathematically how work and energy are calculated. We're going to do some homework problems as well, and we're going to move on to look at what gravity does in terms of transferring energy, and that's a very interesting topic to look at, but we will be there in our next lesson.